Now we're handing over to Professor Rami Abou Jamra with the second part of our workshop here, who will present why exome analysis is his method of choice when diagnosing intellectual disability. So I'm happy to introduce to you all Rami Abou Jamra. He studied medicine in Damascus and completed his medical education in Bonn. Between 2010 and 15, he gained further experience, scientific and clinical experience in Erlangen and Rostock, also in Germany. And since 2015, he's the head of the diagnostic department at the Institute of Genetics, the University of Leipzig Medical Center. His focus is on genetics of intellectual disability and the development of new applications for routine diagnostics. So Rami, you have been using exome sequencing from very early on. When did this start?
Hi, Yvonne.
Hi.
This was in 2010 as I moved to Erlangen. Actually, I moved to Erlangen because I've heard they are doing that. At that time, I was doing linkage analysis and identifying candidate regions where the mutations must be located in, but then there were like 60, 70 genes inside, and I started doing this per Sanger. It was very expensive, very exhausting, and I did not find the mutation. So I moved to Erlangen, where in March 2010, I have done my first 16 exome sequencing of cases of children of intellectual disability with good linkage region. And this was really successful because of these, I have almost published all of them.
Nice. So at the beginning, exome sequencing was a research application for you. So when did you make the transition to clinical diagnostics?
Well, and that was the reason for my next switch, because in Erlangen, I realized that exome sequencing is still research, although it was good enough to move to diagnostics. So I moved to a private laboratory where I knew they are performing exome sequencing. So they had a couple of dozens as I arrived, but within 1 year we have performed 1,000 exome sequencing. And I would say this was the point where I was sure what I felt before in 2013 and 2014 that exome should be a diagnostic tool. I have been able to apply this in 2015.
So when you started in Leipzig, 2015, what were the challenges? How has NGS-based diagnostics evolved in Leipzig since then?
Yeah. At the end of 2015, I arrived in Leipzig, and at that time there was no machine for sequencing and there was no software to analyze the data, but there was the expertise how to analyze the data. And what we have done at that time is we decided we want to do the diagnostic even if we don't have the tools at house, so we outsourced that. That means we were sending our DNA to be sequenced somewhere else. We were sending the data to you to be analyzed somewhere else. And then we were getting back the clinical data and the genetic data, and we were able to do the analysis. So we were able to do exome diagnostic in a one-man show, because you don't need more than that. You can outsource whatever you cannot do by yourself. The expertise is realizing what this data says, and if you have this, you can run exome sequencing.
So let's take a look at your slides then. I will hand over the slides to you.
Fine. As we have, I'm going to jump over some slides in cases where I think that we are running out of time. I also have some polls. I would be happy if you would join me in the polls, but because of this delay, maybe it would be less satisfying. So don't be bothered if I go on. Just take a look at your mobile. Whenever you see a question, just answer directly. Don't wait until I say something, because I will be 30 seconds later than what you see on your mobile phone. So I don't have, now. Well, I wanted to show how we performed in Leipzig. In 2000, and I arrived in 2015, end of 2015. In 2016, we directly started doing exome analysis. We were doing also some panel analysis, but we were doing only few cases. And we had also some panels like epilepsy panel for epilepsy cases, like 100 genes, the same for cancer. This OMIM panel is actually the TrueSight one. This is about 5,000 genes. Some people call it also clinical exome. And year for year, we were getting better and performing more of epilepsy. The same study about cancer, because that was a steady income of cases. We were doing more OMIM and also more exome. And then the cancer was steady. Epilepsy, we found 100 genes for epilepsy. Like what there are like 1,000 genes for epilepsy. It doesn't make sense to make a panel of 100 genes, so it got less. While OMIM was getting better, and exome was getting also more, but less aggressive. The reason is the machines or the costs for performing OMIM panel were less. So in 2019, we omitted small panels. We were only doing larger panels or exome diagnostic. The cancer was still steady. And then in this year, we stopped OMIM fully. The few cases here in OMIM that you see are actually cases that were done in 2019. This year, we are going to do about 2,000 cases of exome sequencing. Some cases of these are even trio-exome sequencing, and besides doing cancer cases, we are not going to perform any panel diagnostic anymore. So why we decided to do this is because we thought exome sequencing has a much better yield. And before I show you about our results regarding the yield of exome sequencing, I thought to know how is your experience with exome sequencing, or how many of these are you performing per year. So we, as I told you, we have done 2,000, or we are going to do 2,000 this year. This is going to get more next year, but we started smaller, and I would say that you don't need much more expertise to do 100 or 2,000. The principle of it is the same. There are some people getting inside. There are some people also doing more than 1,000 cases a year. That's interesting. I have to move to slide, I'm sorry. And why we are doing exomes and why we are doing less panels? Well, first reason is the yield. When we are doing an OMIM panel or a clinical exome or whatever you want to call it, a few thousand of genes, then we have a diagnostic yield of a little bit more than a quarter, like something about 22%. When we are doing exome sequencing, then we have much better. It's more than a third of the cases are solved. Something about 35% of the cases are solved. So we have like 50% win of diagnostic yield. And I think this is enough reason to omit every panel and go to exome, because there is no perfect panel. If you now design a panel, it's next week, it's already too old. While doing an exome gives you the chance that you update your in silico panels. But there are also, in my opinion, many other reasons why one should use exome diagnostic. And I'm sorry, and before I move to further reasons, I wanted to see what is your experience regarding the yield, the diagnostic yield in this case, or do you think that something about 35% that I'm talking about is reliable, or do you have much less yields? I know some people who would say they have more than 50%, and I get, oh, okay, is this possible? But obviously, it may depend also on the phenotype or what diagnostic has been done in advance, because, I mean, of course, the yield is less if you have done everything else before starting an exome, and it's higher if you're starting with exome, etc. But I see that people up to 40%, that is more than 20% anyhow, that is like the average that we also see in our cases. Another reason why we are using exome, it's really rapid, it's really quick, and it encompasses always all possible cases. Here is a clinical phenotype from our laboratory. It's a case of a rare and unspecific phenotype. A girl, 7 years old, and she was born in the 41st gestational week, very normal. Birth weight and length and head circumference also normal. And in the first month, there was nothing that is remarkable. However, however, she spoke her first words with 2 years, which is a little bit too late. And in addition, the muscular hypotonia and the development, the development of her continued to be a little bit slow. So she has got diagnosed a neurodevelopmental disorder of a mild and unspecific form. She has only one cafe au lait spot, and one spot is no spot. And nothing else, no epilepsy, growth is okay, no malformations, and that's it. So this is one case where it's impossible that you do a specific diagnosis and find the mutation, because hundreds of genes may lead to this phenotype. And what we have done is try exome sequencing of the child, the mother, and the father. As we have done that, we found or identified only in the child 82,000 variants. And when we are doing such an analysis on a diagnostic base, it is really tough to analyze all these variants. So we make a first reduction step of variants, which we find very useful, and that is we apply a so-called in silico panel. And the panel that we most of the time use is our morbid gene in silico panels. So that means we analyze only genes that have clinical relevance. So we take genes that have an OMM phenotype, or genes that have more than 3 likely pathogenic or even pathogenic variants in ClinVar, or that they have more than 3 likely pathogenic variants in the HGMD. And we think that taking all these criteria together gives a good reflection of the panels. I give you an idea about how this panel look like. Genes that fulfill all 3 criteria are here, and gene fulfill 1 of 3 criteria are here. And if we take the sum of them, then we have about 4,096 genes that are in the latest version of our in silico panel are morbid genes. These are genes that for sure have clinical relevance. So when we do our analysis, if this is the 20,000 genes that we have, we analyze only a quarter of them, or 20% of them, and we omit, at least for the routine diagnostic, the remaining genes. That means in this case, we don't need to check all genes, but only 20,000 of these. And then we do very simple filtering steps. We take variants that have an impact on the protein, and high or moderate impact on the protein, that have at least a moderate quality of sequencing. That means they are not artifacts. In this case, we check the de novo with a prevalence in the general population about 0. We don't take exactly 0 so that we avoid any artifacts in the general databases. And when we click all these 4, then we have within seconds our variant in the gene SRCAP. We have a de novo variant. The alternative allele frequency is 0.33. A third of the reads in the child were carrying the change that is leading to this variant, to this frame shift. So it seems like if it's a mosaic, that means the variant came after, it was a post-psychotic variant after the fertilization of the oocyte. And the report would look like this. Index and parents. Phenotype is a global developmental delay with muscular hypotonia. And the child has a proximal SRCAP related disorder. We describe the variant, and then we get with the smaller text. I think that the session is registered, so you can read this slowly later. But the most important thing inside here is that there are only few cases worldwide with variants in SRCAP. So this gene is practically included in no panel. And if we don't have, if we didn't perform an exome, we would never have identified that. So we find such a rarity, something such extraordinary and very rare in analysis that takes literally 20 seconds. Another reason why exome sequencing is a good idea is you can omit arrays. You can omit array CGH, or you can omit also the SNP array. I'm going to present you a case with a tiny deletion that we have identified using exome sequencing. It's a 2-year-old boy, and born in the 41st gestational week. And he was, as he was born, a little bit too big, but well, on the 97th percentile. And otherwise, there were no remarkabilities. However, the neonatal adaptation wasn't good, so he stayed in the neonatology for a few days. Later on, everything was good, and the child sat down by age of 10 months, walking with 24 months. That is a little bit later than normal, but not a catastrophe. First words also a little bit later, but also not a big issue. However, at the age of 2 years, as we have seen the child, he didn't have two-word sentences, so the child has once again an unspecific mild developmental delay. And so the diagnosis neurodevelopmental delay indicated running a diagnostic, and we went for exome sequencing. And in this case, there was no point variant, but we checked the copy number variants, and we see a deletion within the gene CAMTA1. So the exons after and the exons before are still there, and we have the deletion inside there. And it's also a pretty simple filtering step so that one can identify this variant. And we could also we can also diagnose this case, something that we wouldn't have been able to do if we are running panel diagnostic and even using an array diagnostic. Not every array would identify such a short deletion because it's only a few exons and they are just neighboring. The variant was de novo, and we were done with that. And then my question once again to you, what we do in Germany, or what in Germany is very often done, is that you are the smartest if you can do a specific differential diagnosis, so that you can start with that. But that's often very difficult, as an example in the case of this child. And what is then said, if you have cases of developmental delay, perform first karyotyping, a very normal chromosome analysis, then perform ACGH, and then a gene panel. And we think in Leipzig, we think this is incorrect. It doesn't make sense to do that. And what we do is we start directly with exome diagnostic, because that gives by far the best result. So what is your opinion on that? How do you perform in your clinical day? And I say here that, all right, I need to take out. So, that most of you are performing small NGS panels. Okay, exome is getting better. And yeah, that's nice. I think this reflects also how many people in Germany are doing that. What we have done also is some validation of the Cnb analysis, so that what the analysis that I showed you is a good one. I'm not going to go into details in that because of the time. I want only to tell you that we have done a retrospective validation of things that we have done before, and also a prospective validation. Ben has spoken about validation studies on that, and I can assure that exome sequencing can easily replace array and makes the diagnosis quicker and more accurate and cheaper. Another reason why we are performing exome sequencing, we are an academic institution, and actually our first goal is not diagnostic, but our first goal is research. So we think that exome analysis supports research. This is an example of a girl who deceased, passed away at the age of 1 month. She had infantile onset of seizures, epileptic encephalopathy, and her sister, her older sister, had the same. She deceased at the age of 5 days with an infantile onset of seizures and epileptic encephalopathy. We performed exome sequencing. We did not find any variant in the panel that I showed you before, in the morbid gene panel. So we expanded our analysis and we analyzed all genes and not only the 4,000 clinically relevant genes. And we found in gene GLS a homozygous variant, a homozygous frame shift variant. We were able to find another case a few months later. So we put our data together and we were able to identify a novel disorder of a glutaminase deficiency that leads to lethal form of neonatal epileptic encephalopathy. And since we have made this publication, this is now a novel entrance in OMIM, and the gene GLS and the syndrome is a part of OMIM, and it helps other people by the diagnostic due to our publication of 2019. And this publication is not an exception. I encourage all of you to do that, because since we have started exome sequencing in Leipzig, I'm only putting things that I was involved in, but there are other people here. Within the last 5 years, we have almost 60 publications of novel disorders. Many of them we are only contributing. You can't do by yourself 60 publications in 5 years, but everybody of you who is performing exome sequencing can be part of this effort. And that's the reason why we always encourage people, if you are doing exome sequencing, you don't only have the advantage of being able to do a better diagnostic, but even if you do not find a mutation in a clinical pattern, you are able also to continue and do research on that, which is valuable for yourself, your career, but also for the whole international community. And I see that, well, I expected that. That's interesting. Most of the people do patient care, but if something went on and you can do research, then why not? So another question directly, if you cannot solve a case that is presented to you, what do you do? What we do is we try to pool data. We send our variants to everybody. We have our variants online, our candidate variants, so that people can check it. We answer emails if somebody is asking us, and we think that sharing information would lead to a better result. But how do you proceed if you have cases where you have something novel, a variant or a gene that nobody has seen before, and you want to know how this works? So you get second opinion for single cases. That means one calls a colleague and asks, what do you think about that? And I see that less people are using Matchmaker, but like companion cohort and other aspects have more priority. Interesting. We indeed go first for Matchmaker, and then we do, if it's about something new, interesting. So at this occasion, I can only take the chance to address you in Italy, to ask you and call you for research. We invite you to do research as a side product of your exome diagnostic. You can check, if you want, our list of candidate genes. We have a couple of hundreds of novel candidate genes on our website. See if something would fit. If you are unhappy to work on your candidate genes, then you can send us also yours, and we will do it together. You can also, if you have exome data but just don't want to bother yourself, you can send us the data and we reevaluate it, and if something gets out of it, we will inform you. So we offer all modalities. Basically, we are very much interested in sharing data, because that is the only way to decipher the genetics of rare disorders. Another aspect is why performing exome sequencing. While I'm saying that, you have probably the slide of the poll, so take part of that. That's interesting. We have, in this case, as an example, what I want to show you is a 7-year-old child, a boy who has developmental delay, autism, microcephaly, and facial dysmorphism, and we have performed a tri-exome analysis, and this child has two de novo variants. Both are likely pathogenic in 2 different genes, TRP12 and TRIOR. If we didn't perform trio exome analysis, we would never identify that, because by the time we have found TRP12, we would think, okay, we are done. And differences between the phenotype of the patient and the known phenotype of the gene, we would rather think, okay, this is because of the normal variability of the phenotype. So what I want to address in this case, if you do your diagnosis diagnostics. You get a diagnosis that does not really fit, then it's maybe due to the dual diagnosis and not because the phenotype is so variable. Of course, there are cases where the phenotype is variable, but this is not always the case. And before I tell you the number that we have identified in our cohort of a couple of thousand of cases, I want to know what you guess how many patients get a dual diagnosis. What I call dual diagnosis is a report where we report more than one variant which we think they are relevant, and we report restrictively. So out of 100 positive reports that we sent, how many reports have one variant and how many reports have two variants, and we think that both variants are relevant? It's not reporting things just to be sure one is on the safe side. That means, in other words, of all people with a genetic diagnosis, how many of them have indeed two diagnoses? I see less than 1%, almost nothing, 1 to 5%, and can show you our numbers, 6%. We think that every 100 persons who has a genetic disorder that is diagnosed, I'm talking only about the 35% of cases that we have diagnosed, 6% of these have a second disorder, and this is massively high. And as we are on that, let me get the question on what you think, how many secondary findings one would identify. A secondary finding, for people who don't know that, is the identification of a variant based on the ACMG that one would report, that is a variant in one of 59 genes that are actionable, usually tumor syndromes or cardiac arrhythmias. And these variants must be pathogenic or likely pathogenic. That means the identification of a variant that would demand that one would go for a clinical management. As an example, if you have a variant that would lead to hypercholesterolemia, then you need to start with statins if you want to avoid a heart infarct. Almost none, less than 1%. 1 to 5% is a third, and the rest are 2/3. Indeed, our number says 3%, and I'm pretty sure of these numbers because we have information from other big labs and also from the literature. 3% is a very reasonable number, and that means of all patients that come in, at least 3% of them get out with a genetic result that is very much relevant for their life. A woman who has mutation in BRCA1 needs to know about this information in order to avoid getting cancer in an early age. And finally, exome sequencing solves tricky cases, but I'm going to jump over that so that I leave 2 or 3 minutes in case there are some questions. As exome sequencing would solve tricky cases, that's something no. In this case, I wanted to present something with a very known variant in PRRT2, but that's not enough for the phenotype. And then in addition, we find that PRRT2 has a de novo deletion in it, which is a rarity. I know it's a rarity, but that is the proof of the quality of your diagnostic, and such a thing wouldn't have been found if you are performing a panel analysis. So the diagnosis is an autosomal recessive form of PRRT2 and not the usual autosomal dominant form. So taken together, I consider that performing exome, and very soon, I think within 1 or 2 years, genome sequencing as a first step diagnostics is a chance to find a good, to find the diagnosis of your patient, to help them. But it's also a duty. Why it's a duty? Well, you can do it. So you must do it if you want to be fair to your patients. Thanks for your attention. For any questions or feedback, I'm now available here. Also Ben, I think. And if you have questions for later on, don't hesitate to send me an email. And yeah, thank you for your attention.
Okay, thank you very much, Rami, for showing these very nice cases. So this takes us to our Q&A session. We have only a few minutes left, and I see these were the questions that were raised in the in Slido. Can I analyze more than 4 family members with your software, Ben?
Yes, of course you can. So there's actually virtually no limit of this to the size of the family. As soon as you add another family member, you are presented with a combined view of all the data sets, and you can filter accordingly, which makes this very convenient.
Okay, second question. How many samples samples do I need to validate my exome analysis assay? Also for Ben?
Okay. Well, this depends on your requirements, how narrow the confidence intervals should be. The more samples you include into your validation, the more the surer you can be about the result. So we can give you, depending on the assay that you're performing, we can give you some recommendations how many samples there should be. But there's no fixed number to be given. 40, as you saw in my presentation, is a good number to narrow down the confidence interval.
Okay, very nice. And when will whole genome take over? Rami, you've already mentioned this briefly. What do you think?
I cannot promise, but I think that in 2022, we are going to do more genomes than exomes, but that is only a guess.
Okay. Last question. Can I use own existing enrichment kits, or do I have to purchase kits from you, Ben?
We do not sell any chemistry or enrichment kits. Of course, we can make recommendations. We have a good overview of the market, which kits perform well and which do not perform so well. And but we can discuss this basically according to your own diagnostic requirements.
Okay, nice. I think this is what we, the questions that have arrived. Before we close, I would briefly want to mention the meeting sessions that are available at our varvis booth at the SIGO conference, where we offer software demos for our Cnb analysis, our West trio analysis, and also a very general demo where you can also ask all the questions that are still open. And for more information and upcoming webinars, please visit our website, and more information to come soon. I thank you all for your time. Thank you, Rami and Ben, for sharing your interesting data here, and wish you all a very nice SIGO conference. Bye-bye.
Thank you. Bye-bye.